doing something different. Using Colab, I'll just read the bot. Unless there's a human who wants to interact, I'm happy to answer any questions, specifically about the current content on bionicchaos.com. Otherwise, if there's no human available, I have to talk to the robots. So apologies in advance. We'll do Notebook LM. I just gave it a summary of what we were doing in Colab. This notebook in Colab. So let's listen to that. It's only 11 minutes.
Have you ever really peered into the intricate dance of electrical signals that is your own brain?
It's pretty fascinating stuff.
Today, we're taking you on a hands-on deep dive. We're looking at the practical side of working with raw brain activity data, the actual foundation of brain-computer interfaces, or BCIs.
Yeah, our mission here is really to walk you through those first crucial steps. Like, where do you even find this data?
Right.
How do you download it successfully? Then how do you prep it? And maybe the most exciting part, how do you actually look inside and understand what you've got?
Think of this as your shortcut, your express lane maybe, to getting genuinely well-informed about how BCI research actually starts. We're aiming to turn these potentially dense technical steps into something more insightful, maybe even uncovering a few surprises along the way.
Okay, so let's talk about that quest for data. The first hurdle is actually pretty significant, finding a public data set that, well, works.
That you can actually download and use?
Exactly. We were looking specifically for SSVEP, that's steady state visual evoked potential, or VEP data, or even just general BCI stuff. But finding a working download link, that can be surprisingly tough.
Yeah, I imagine you hit some dead ends. Broken links, outdated servers.
Oh, definitely. You find links that just go nowhere, or data sets behind logins you can't get anymore, or files that are just so old they don't play nice with modern tools.
So what was the breakthrough?
The breakthrough was finding the EEG motor movement imagery data set, specifically one file, S001R01.edf. We found it on PhysioNet.
Ah, PhysioNet. Good resource.
Fantastic resource, really reliable, well-maintained. We were pretty happy to find that.
Okay, so we had the link.
Step two.
Actually getting the signals right, downloading. We used wget, which is, a pretty standard command line tool.
Yep, nice and simple. But then came the first, let's call it a practical data moment.
Right, the download finished, and we had a file named ssvpdataset.zip. Looked like a standard zip file.
Exactly, looked like one. But when our system tried to, peek inside expecting compressed stuff, it wasn't a zip file at all.
No. What was it then?
It was an EDF file, European data format. The system was smart enough to flag it, actually. It identified it specifically as BioSig-DF.
BioSig-DF. Okay, so what does the BioSig part tell us? Is that significant?
It is, yeah. It basically confirms the file follows a recognized standard for biological signal data within that EDF structure. BioSig itself is a whole toolbox for processing these kinds of signals.
I see.
So seeing BioSig-DF is like a stamp of approval. It means, okay, this is probably a well-structured file, and it should work with standard analysis tools, like the one we use later, MIBNE.
Gotcha. So a little detour, but an important one. The solution was simple then. Rename the file from ssvdataset.zip to the correct name, S0001R01.edf.
Yep. Straightforward fix, but it highlights something crucial about working with real-world data, especially public data.
Don't always trust the label on the tin.
Right. Exactly. You've got to verify. Always peek under the hood. Mislabeling happens more than you'd think.
And this file, was it huge? Did it take ages to download?
No, actually, that was another nice surprise. It was pretty small, just 1.2 megabytes.
Oh, tiny.
Yeah, downloaded in 2.1 seconds. Super quick, but still packed with useful brain data.
Okay, so data secured, file name corrected, we're ready to actually meet the data. What tool did we use to finally look inside this EDF file?
Right. The key player here was the Mine library. It's a really powerful Python library built specifically for EEG and MEG analysis.
Magnetoencephalography, right?
That's the one. And like a lot of these specialized tools, you often have to install it first. That's just a standard first step in data science work.
Sure, setting up your environment. So Mine installed, we load the file. Did it work smoothly?
It did, thankfully. Loaded without any errors. And right away, we started getting the basic specs.
Like what? What were the first things we learned?
Okay, first confirmation. Loaded successfully. Good start. Then channel count. 64 channels.
64. So that's like 64 little microphones listening to the brain's electrical activity.
Pretty much, yeah. 64 listening posts spread across the scalp. Gives you decent spatial coverage, where things are happening.
And what about how fast it was recording?
That's the sampling frequency. It was 160 hertz. So 160 data points every single second for each of those 64 channels.
Wow, okay. 160 snapshots a second. That's pretty fast. Why so fast?
Well, you need that speed to capture the really quick changes in brain activity, those subtle fluctuations, especially for things like evoked potentials. They happen fast. 160 hertz gives you good temporal resolution.
Makes sense. And how long was the recording itself?
The whole file covers about 61 seconds of recording time.
Okay, about a minute. And we saw channel names too, right? Things like FC5, C3, CZ, O1, Oz, O2. They looked kind of technical.
They are, but they're standardized. Those names tell you exactly where the electrode was placed on the head according to the International 1020 system or variations of it.
Okay. So F for frontal, C for central, O for occipital, back of the head.
Exactly. K's is right in the center top. O1 and O2 are over the visual cortex area. So the names directly link the data channel to a physical brain region, which is obviously super important.
And then we actually looked at the raw numbers.
We did. Just a tiny snapshot, the first 5 data points from the first 3 channels. And you see these small numbers like Niediger 1.6E05 after 5.6E05.
Microvolts, right. Tiny voltage changes.
Precisely. Those are the actual measurements of the brain's electrical field, fluctuating over those tiny fractions of a second, defined by the 160 hertz sampling rate. That's the raw language of the brain we're trying to decode.
Okay, so we've got the data loaded. We know the basic specs, channels, sample rate, duration. How do we start to see this? How do you visualize raw brain signals?
Well, the most direct way, especially with Hen, is just using its built-in plotting function. We use raw.plot.
And what did that show us?
It lets you visualize the waveforms directly. We plotted, I think, 5 channels over a 10-second window. And boom, that's where you see the brain waves, those squiggly lines going across time. It makes the numbers tangible.
Right, you see the ups and downs, the rhythms. But when we were thinking about visualization, we hit another one of those aha moments, didn't we, about choosing the right kind of visualization.
We did.
I mean, coming from general data analysis, my first instinct might be, I don't know, can we use a Venn diagram to group channels or something? But that doesn't really work for this kind of data, does it?
Not for the raw time series data itself, no. You're right, we did sort of conceptually group channels. Thinking about these are frontal, these are parietals. And a Venn diagram could illustrate those groupings, sure.
But it doesn't show the actual brain activity over time.
Exactly. It's a way to categorize the sensors, not visualize the signals. The core thing with EEG data is preserving that time dimension and the amplitude changes. Static diagrams like Venn just don't capture that dynamic flow.
Okay, that makes sense. And what about something like a knowledge graph? They're great for relationships.
Also powerful, but again, for a different purpose here. A knowledge graph would be excellent for mapping the metadata.
Like linking the subject ID to the recording date, to the channel names, to the sampling frequency. That kind of information network.
Precisely. Mapping the relationships between the descriptive fields about the data, not the time-varying signal values themselves. It's all about using the right tool for the job, what aspect of the data you want to understand or communicate.
So if not Venn diagrams or knowledge graphs for the raw signals, what are the typical, more appropriate ways to visualize EEG? You mentioned the raw plot.
Right, the raw plot is fundamental, but beyond that, you often move to things like spectral plots or spectrograms.
Looking at frequencies, like alpha waves, beta waves.
Exactly. Those show you the power or intensity of different brain rhythms over time. Then there are topographical plots, topoplots.
They look like heat maps on a head shape.
That's them. They show the spatial distribution of activity across the scalp at a specific moment or averaged over a time window. Super useful for seeing where activity is strongest. And of course, for things like VEP or SSVEP, you'd look at evoked potentials averaging the signal lock to specific events to see the brain's consistent response.
Got it. So specific tools designed for the specific nature of brain signals. So bringing this all together then, we found the data, downloaded it, fixed the name, loaded it with May, checked the channels, sample rate, saw the raw numbers, and even visualized the waves. What's the big takeaway for someone listening? What does this all mean?
The really critical takeaway, I think, is that by doing these steps, we now have the data loaded and initially understood. It's in a state, a format, that's ready for standard EEG or BCI analysis using powerful libraries like MNE Python.
We've crossed the first major hurdle.
Exactly. We've laid the groundwork. The data is now tractable, ready for the next phase of actual scientific investigation.
And what would those next steps typically be, according to our sources anyway?
Right. The typical workflow from here involves pre-processing. That's a big step.
Cleaning up the data.
Essentially, yeah. You'd apply filters to remove unwanted noise like electrical grid hum or slow drifts. Then artifact removal, trying to identify and remove signals that aren't brain activity, like eye blinks or muscle tension.
Stuff that can contaminate the real signal.
Precisely. After cleaning, you'd often do ipapping.
Which is like chopping the data up.
Kind of. It's segmenting the continuous recording into smaller chunks or epochs that are time-locked to specific events in the experiment. Like if it was a visual task, maybe you'd create an epoch around each time a stimulus appeared on screen.
Okay, so you isolate the brain's response to specific things.
Exactly. And then with that clean, segmented data, you can finally dive into the specific analysis, calculating SSVP frequencies, looking for VEP components, training a BCI classifier, whatever the research goal is.
So it really is a process. Getting the data is just the beginning.
Absolutely. It's fundamental, but it sets the stage for all the deeper analysis that follows.
Well, that was quite a journey from just searching for a data set, navigating that zip file confusion.
Yeah, the little surprises.
To actually loading it, seeing the channels, the speed it was recorded at, and getting that first glimpse of the raw brain activity. We've covered that essential first stage.
And hopefully shown that while there are technical steps, they're manageable, and understanding them is really key.
It really is. Knowing these foundations helps unlock the potential for understanding the brain better and for developing these BCI technologies.
So maybe a final thought for our listeners. Now that you've sort of seen under the hood, seen what raw brain data looks like and the first steps to handling it, what kind of questions start popping into your mind? What could we potentially answer? What cool applications might be possible once we really start decoding these incredibly complex signals?
That's a great question to ponder. What can we unlock next? Yeah, definitely something to think about until our next deep dive.
Yeah, so there is a human in the loop just trying to pass this data set.